Mathematical induction in its most basic form is often used to prove statements that depend on a natural number n. Here we use the convention that the natural numbers begin at 1. For example, 2 to the n greater than or equal to n squared for all natural numbers n is such a statement. In order to prove something like this using mathematical induction, what you need to establish are the following. The first is, the statement holds for the case when n is equal to 1. This is called the basis or the base case. The second is, assuming that the statement holds for n equals k for some natural number k, the statement also holds for n equals k plus 1. This step is called the inductive step, and the assumption that we're making here is called the inductive hypothesis or induction hypothesis. To get an idea why this is sufficient to prove the statement for all natural numbers n, suppose that the basis has been established. Now, if the inductive step is also established, then that means the statement must be true for n equal to 2 because it is true for n equal to 1, and the inductive step tells us that the statement must also be true for n equals 1 plus 1, which is 2. But now we can apply the inductive step again. We know that the statement is true for n equals 2, so it's also true for n equals 2 plus 1, which is 3. You can keep applying this reasoning, and you'll see that the statement is true for any arbitrarily large values for n. So this is like falling dominoes. So let's use this technique to prove the following. So we're going to prove that the sum of the first n natural numbers is given by n times n plus 1 divided by 2. So let's look at the base case. When n is equal to 1, the left-hand side is just 1, and the right-hand side is 1 times 1 plus 1 divided by 2, and that's also 1. So the left-hand side is the same as the right-hand side, so the statement holds for n equals 1. Now let's establish the inductive step. So we assume that the statement holds for n equals k for some natural number k. That is, we assume that the sum of I when I ranges from 1 to k is given by k times k plus 1 divided by 2 for some natural number k. Now we want to prove that the statement holds for n equals to k plus 1. So the left-hand side is the sum of I as I ranges from 1 to k plus 1, and that can be broken down into the sum of I as I ranges from 1 to k plus k plus 1. But by the induction hypothesis, we know that this is just k times k plus 1 divided by 2. So we can replace that with k times k plus 1 divided by 2 plus k plus 1. And if you work this out, this is the same as k plus 1 times k plus 2 divided by 2, which can be written as k plus 1 times k plus 1 plus 1 divided by 2. And this is precisely the right-hand side of the statement when n is equal to k plus 1. So we have established that the statement holds when n is equal to k plus 1, assuming that the statement holds when n is equal to k. So we have established both the basis and the inductive step, and by the principle of mathematical induction, we conclude that the statement holds for all natural numbers n. Now, as an exercise, try applying mathematical induction to prove this statement. You will see that you cannot do it because it's not true.